This is the AQA AS Chemistry Paper 2 from 2018. There's a few general examiners' reports comments about this paper. I'll repeat some of them as we go through the paper, but generally it said the students should be more familiar with the practical work that they've carried out during the 2 years of A-level, including why they carried out certain procedures, not just how. Again, I'll highlight what they mean by this as we go through some of the questions. Students also need to understand the appropriate precision that they're to give in their answers. Know that covalent bonds don't break when melting or boiling. Be able to deduce the structure of repeating units of polymers, and also convert ratios into the simplest whole numbers when we're deducing things like empirical formula. Question 1 is about hydrogen peroxide decomposition. So we're given the equation here, and we're told that it's carried out in the presence of a catalyst, in this instance manganese oxide. So there's 3 experiments which carried out, shown in figure 1. They were carried out to investigate how the volume of oxygen produced varied over time under different conditions. The mass of the catalyst was the same in each experiment, so we know we don't have to worry about the amount of catalyst. So we can see with the 3 experiments, the first 2 differ in just that the catalyst was in lumps in the first and then powder in the second. And the first and the third experiment differed. Lumps were the same as the catalyst. We have the same temperature, we have the same amount of hydrogen peroxide, same volume. It was just that the concentration was half in experiment 3 than experiment 1. So we've got figure 1 shows how the volume of oxygen collected varied in time in experiment 1. So we're given a graph there of volume of oxygen against time. So part 1 said explain in general terms of how a catalyst increases the rate of reaction. And again, it says in general terms about a catalyst. So it wasn't asking for example, heterogeneous or homogeneous catalysts. It was just saying, in general terms, how does a catalyst work? So there's 2 important parts that you've got to get when you're asked a question about catalyst. First off, what catalysts do is they lower the activation energy. And a lot of students get this, but also whenever you've got a question about a catalyst, how a catalyst works, you've also got to include that they lower the activation energy by providing a different or alternative pathway. So it's a standard question about catalysts, and it's a standard answer. You've got to make sure that you get in about lowering activation energy and providing a different pathway. So part 2 says draw 2 lines on the figure 1 to show how the volume of oxygen collected varied with time in experiments 2 and 3. Label each line in the experiment number. So if we go back to the diagram, so we've already got the line for experiment 1. So how does it differ with 2? Well, we've got the same amount of hydrogen peroxide, both in terms of concentration and volume. The temperature is the same. The only difference is that it's a powder. Now, because it's a powder, it means the catalyst is going to be more effective. So it's going to speed up the reaction even more. But because we've still got the same amount of peroxide present, the amount of oxygen that's going to be released in the end is going to be the same. So we're going to end up with the same amount of oxygen. It's just going to get there quicker. So what we need to do is, again, we're starting with 0 oxygen. But the line is going to be steeper because the reaction is happening quicker because we've got a powder instead of lumps. But if it's still going to level out at the same amount of oxygen because we've got the same amount of peroxide. So if we label that experiment 2. So all that's happening in this experiment is, because it's a powder, the reaction is occurring faster, so we've got a steeper line, but we're going to have the same amount of oxygen that is released. Now with the third experiment, we're back to lumps, so the catalyst is going to act in the same way, but because we've got half the concentration of peroxide, then ultimately we're going to end up with half the amount of oxygen released, but also it's going to get there quicker because there's fewer molecules per volume. Then there's going to be less successful collisions, so the rate's going to be slower and we're going to end up with less oxygen. So we're going to end up, rather than it be 4 squares, we're going to end up at settling out over here somewhere, but it's going to get there slower too, so the graph is going to be less steep and then level out at 2 of these squares rather than 4, because we've got half the amount of peroxide available to us. So again, we'll label that number 3. Right, question 1.3 says, explain in terms of collision theory the effect of increasing the concentration of hydrogen peroxide on the reaction rate. So I've already mentioned this answering the last question. So if we increase the concentration of hydrogen peroxide, what it means is there's more molecules per unit volume. So if we take a set volume, concentration means there's going to be more particles there. So because there's more particles in the same volume, there's going to be more frequent successful collisions. Now you've got to put in the terms frequent, because a lot of students just put there's more collisions, but that we're talking about reaction rates, so we've got to talk about rates of collision. It's no good just to say there's more collisions. We've got to say there's more frequent collisions, but also we've got to say that they're successful, because if those particles don't have enough energy, again, they could collide, but they're not going to react, so the reaction rate's not going to go up. So the key things to include here in your answer are not just that there's more molecules per unit volume, but the collisions are more frequent and those frequent collisions are more successful. So if we put that down, we can say as more molecules in the same volume, by increasing the concentration, there'll be more frequent successful collisions. Question 2 is about citric acid. It says a student analyses a sample of citric acid to determine its percentage purity. The student dissolved 784 mg of impure citric acid in water to prepare 250 cubic centimetres in the volumetric flask. The student then titrated 25 cubic centimetres of the sample of this solution with 0.05 moles per dm cubed sodium hydroxide using phenolphthalein as an indicator, and we've got a equation there. Now, thing to note here, for every citric acid it's going to react with 3 sodium hydroxides. So part 1 says the student rinsed the burette before filling with sodium hydroxide solution. State why the student should use sodium hydroxide solution rather than water for the final rinse of the burette. Now, this is an example from the examiner's report where they said that students need to understand why they carried out certain things, not just did it. So when you carried out an experiment like this during your A-level, you will have rinsed out with, say, sodium hydroxide, and students are able to recall doing that, but many students don't know why they did that. So in this case, if they used water, it would actually dilute the sodium hydroxide once you put in, because there'll be some remaining water there. So when you fill up with sodium hydroxide, it wouldn't be the true concentration, it would be a diluted version. So for an answer for this, we can put use of water would dilute the sodium hydroxide. So it says the student carried out several titrations. The results are shown in table 2. Complete table 2 to show the theta of each titration. So it's just subtract the bottom number from the top. So in this case, we've got 25.2. The next one will be 23.90, then 23.70, and 24.00. Now, the key thing here to get all the marks is the use of decimal places. So we see in the first one, the rough one, we've only got 1 decimal place in our data, so our answer is to 1 decimal place. But in all the others, the data is given to 2 decimal places, therefore our answer has to be to 2 decimal places as well. So this is calculate the mean theta using the concordant results. Give your answer to the appropriate numbers of significant figures. So what we've got to do here is work out which of those 3 values to use. So in this case, we're only going to use 1 and 3 because sample 2 isn't a concordant result. So we're just going to use those 2 for all means. So add them together and divide by 2, which gives us 23.95, and again to 2 decimal places. Right, 2.4 says the total uncertainty when using the burette is plus or minus 0.15 cubic centimeters. This is a combination of the uncertainties in the start reading, final reading, and the determination of the endpoint. Use your answer in part 2.3 to calculate the percentage uncertainty for the use of the burette in this experiment. So because it's just a percentage, we're going to take the uncertainty, which is 0.15, and we're going to divide that by our mean theta value, which we've just calculated as 23.95. Multiply that by 100, so we get a percentage, so the answer becomes 0.63%. So next we've got a calculation. It says use your answer in part 2.3 to find the mass in milligrams of the citric acid dissolved in the 250 cubic centimeter of the solution, and we're given the molecular mass of citric acid. So remember, it's the mass of the citric acid in our original 250 solution. So first thing we've got to do is work out how many moles of sodium hydroxide we've added to the experiment. So the moles of NaOH equals or 23.95, which we calculated as an average. And what we're going to do, we need to work out the fraction of a litre or a dm cubed that we've added, because we know how many moles there are per dm cubed. So we've got to work out the fraction of a dm cubed to work out the fraction of that concentration that we've used. So it's 23.95 divided by 1000 times by our concentration of sodium hydroxide that we're using, which is 0.05 moles per dm cubed, and that comes out to be 0.001198. Okay, so now we've got the number of moles of sodium hydroxide. We've got to work out how many moles of acid, citric acid, were in our flask or volumetric flask. Now remember, when I was reading out the question, I said that there was a ratio of 1 acid to every 3 sodium hydroxides. So what we've got to do is work out and adjust because of that ratio. So the number of moles of acid would be the number of moles of sodium hydroxide that we've got. So it's 0.001198. But we're going to divide that by 3, because we know that for every mole of citric acid there's 3 moles of sodium hydroxide, and then we're going to multiply that by 10, because during this titration we only took 1/10 of the original amount that was in the flask. We made up 250 cubic centimeters, but each of our titration was only 25 cubic centimeters. So however many moles we can find of acid within our titration, the amount of moles of that are in our volumetric flask will be 10 times that. So that will come out to be 0.003992. So we know how many moles of acid were in our volumetric flask. So now we've got to work out what the mass of that acid is. So the mass of the acid will be the amount of moles of acid we've got times by the molecular mass of the citric acid, which we were given to be 192, and that comes out to be 0.766 grams or 766 milligrams, because we're asked to give the answer in milligrams here. So the final part of this question asks us to calculate the percentage purity of this sample of citric acid. So we know that we've got 766 milligrams of citric acid, but at the start of the question it says that we had a sample of 784. So we added what we thought was 784 grams of citric acid, but it only turns out to be 766 present. So to find the percentage, we take 766, which is our amount, divided by 784, which was the amount we added, multiplied by 100 to get a percentage, and that comes out to be 97.7% purity. Question 3 is about enthalpy changes. So we're told that ethanoic acid reacts with sodium hydroxide and the enthalpy change is minus 56.1 kilojoules per mole. We're given the equation and we're told to calculate the temperature rise when 25 cubic centimeters of 2 moles per dm cubed of aqueous ethanoic acids reacts with 25 cubic centimeters of 2 moles per dm cube aqueous sodium hydroxide. Assume that both solutions have the same initial temperature and have a density of 1 gram per cubic centimeter and the specific heat of 4.1 joules per Kelvin per gram. So first thing we need to do in this is to work out how many moles are reacting. So if we take the ethanoic acid, so we can say that the number of moles equals 25 cubic centimeters, and again, because we're given it in moles per dm cubed, we've got to work out the fraction of a dm cubed we've got. So it's 25 divided by 1000 times by the 2, which is the 2 moles per dm cubed, and that comes out to be 0.050 moles. So next we've got to work out the amount of heat that's been released. So the heat released is 0.050 moles, and we've been told that it releases 56.1 kilojoules per mole. Now we've got 0.050 moles, so it's just the amount in moles that we've got reacting times by delta H, which is 56.1, and that comes out to be 2.805 kilojoules or 2805 joules. So now we've got the amount of heat released, we can calculate the temperature rise. So the temperature rise is delta T equals Q over MC. So Q is the amount of heat released, which is 2805. Our mass is, we've been told that the density is 1 gram per cubic centimeters. Now our total volume is 25 cubic centimeters of ethanoic acid and 25 cubic centimeters of sodium hydroxide. So our total volume is 50 cubic centimeters, and because the mass is 1 gram per cubic centimeter, our mass is going to be 50 grams, and we multiply that by the specific heat capacity that we were told is 4.18, and that gives us a value of 13.4 degrees C. So a lot of students struggled with this question, but mainly in finding the heat released using the enthalpy change and the number of reacting moles. So we're told that that the delta H is minus 56.1, but that's for a mole. So we've got to work out the fraction of 1 mole that's reacting to work out the fraction of the 56.1 that's released. So question 3.2 says a student recorded the temperature of aqueous ethanoic acid in a polystyrene cup for 3 minutes. At the 4th minute, the student added some sodium hydrogen carbonate. The student stirred the mixture and carried on recording the temperature every minute for several minutes. The student's measurements are shown in figure 2. A best line fit showing the temperature before mixing has been drawn. Draw an appropriate best line on figure 2 and use it to find the temperature change. at the time of mixing. Now, if we have a look at this, we can see that straight away that this value here doesn't really fit with the rest of the data. So what we're going to do, we're going to ignore that in drawing our line of best fit. Now, a lot of students did a straight line for this, but it looks more like a curve. So what I'm going to do is do a line of best fit as a curve through these points. I'm going to ignore the time at 5 minutes. And also, I'm not going to go beyond the 4-minute mark, because this is the point where we added the other reagent and stirred it. So to get the marks for drawing the graph, we need to ignore the point of 5 minutes and not extend this line past the 4-minute mark. So in this case, the temperature change when mixing would be what we started off at, which is 17.2. So this up here is 17.2. Then we take away whatever value we've got down here. So let's say that's 11.2. So the temperature change at the time of mixing would be 17.2 minus 11.2, which would give us a change of 6 degrees C. So whatever value you have when you've drawn this curve, that would be the value that you use in there. So question 4 is a question about alkanes. We're given the structure of 2 alkanes here and told that they're found in crude oil and can be separated by fractional distillation. Both can be used in fuels or cracked to form other products. So 14.1, we're asked to state the general formula of an alkane containing N carbons, then deduce the expression of the molecular mass of an alkane in terms of N. So the general formula for an alkane is CnH2n plus 2. And that's something that probably covered at GCSE. So the expression for its molecular mass, we can see for every N we have 1 carbon and we have 2 hydrogens, then another 2 hydrogens. So if we just look at, for every N, we've got 12 from the carbon molecular mass. Because we've got 2 hydrogens, that's going to be an extra 2. So it's going to be 14.0 N plus 2.0 from the extra 2 hydrogens for every N that we have. Right, explain why non-N has a higher boiling point than 2,4-dimethyl heptane. So where a few students went wrong here, so this is all about when we boil a substance, it's all about breaking those intermolecular forces. Now, what doesn't happen when we boil a solution is breaking covalent bonds. They don't break during boiling or melting. So, but a lot of students did put about covalent bonds being broken. But in this case, it's all about the van der Waals interactions between the molecules. So because non-N has more van der Waals forces between the molecules, because there is more surface contact. So because there's more points of interaction in nonane than 2,4-dimethylheptane, there's going to be more van der Waals forces, which of course require more energy to break and pull them apart. Given equation for the complete combustion of nonane. So this is just balancing equations. So the formula for nonane is C9H20, and we know that we need oxygen, and we know the products are CO2 and H2O. So now it's just a case of balancing the equation, and we end up with 14 oxygen, 9 CO2 and 10 waters. Nonane is often found in fuel for jet engines. Combustion in jet engines produces pollutants including nitrogen monoxide. Explain how this nitrogen monoxide is formed. Now, again, the nitrogen doesn't come from the fuel itself, it comes from the air, and it's important to get that across where the source of the nitrogen is, and the oxygen. So the N and the O from the air react at high temperatures. So it's the high temperature that exists during the combustion forces the nitrogen and the oxygen in the air, not the fuel, to then react to form NO. Nonane can be cracked to form large quantities of propene. Name the type of cracking used. So obviously we're cracking it through heat, so it is thermal cracking. Right, so lastly, we said the main use of propene formed from cracking is to make polypropene. Draw the repeating unit of polypropene. So again, as I said right at the beginning of the paper, a lot of students found it difficult to deduce what the repeating unit is of a polymer, and in fact only about 30% of students could do this. So what we need to do is draw the formula for propene, and the way that it forms a polymer is through the bonds either side of this. You don't need, you could put the brackets on, but they would just be ignored during the question. But that would be our repeating unit of polypropene. So question 5 tells us we have a hydrocarbon that contains 87.8 by mass of carbon and has a relative molecular mass of 82. The hydrocarbon decolorizes bromine water. Determine the empirical and molecular formula of the hydrocarbon and suggest two possible structures of the hydrocarbon. Name the type of reaction that takes place when bromine water reacts with the hydrocarbon. So we know it's a hydrocarbon, so if 87.8% of it is carbon, that must mean the other 12.2% of it is hydrogen. So to find out the relative ratios, what we need to do is divide by the atomic masses. So for example, 87.8 is carbon, so we divide by the atomic weight of carbon, which is 12, and the ratio that's going to be to hydrogen is the 12.2 divided by 1, which is the atomic weight of hydrogen, and that comes out to be 7.3 to 12.2. So what we want to do now is divide each of these numbers by the smallest out of the two. So in this case it would be 7.3. So if we divide 7.3 by 7.3 and 12.2 by 7.3, we get 1 to a 1.67 ratio. Now when we've got things, obviously 0.67 is 2/3. So when we've got this fraction that involves thirds, 2/3, etc., what we want to do to be able to get this ratio in whole numbers is multiply through by 3. So if we multiply this ratio by 3, 1 times by 3 is 3, and 1.67 times by 3 is 5. So that gives us our ratio of numbers of carbon atoms to number of hydrogen. So our empirical formula will be C3H5. And C3H5 would give us a mass of 41. So we've been told that in the question that the molecular weight of the hydrocarbon in question is 82, which is obviously twice this. So what we need to do is double the empirical formula to give us the molecular formula. So the molecular formula will be C6H10. We've been asked to draw 2 examples of a structure that would be C6H10 and decolorized bromine. So a couple of examples that we could have would be a structure like this with a double bond there, and we could also have a structure like this, which again would give the same molecular formula. There's other things you could have, for example, dienes, molecules, triple bonds, etc. And the final part of the question was name the type of reaction that takes place when the bromine water reacts with the hydrocarbon. So this will be electrophilic addition. So in question 6, we're giving a halogen alkane and we're asked to name the compound. So first off thing to do is see how many carbons are in the main chain. So in this case we've got 1, 2, 3, 4, 5. So there's 5 carbons. So we know, and there's no double bonds, so we know it's going to be a pentane. Okay, so now we can see that we've got 2 methyl groups on positions 2 and 4, and we have a chlorine at position 3. So the compound is going to be 3 chloro, 2 4 dimethyl, because we've got the 2 methyl groups, pentane. So compound A has a relative molecular mass of 134.5, The main isotope of hydrogen is H1. The main isotope of carbon is C12. But chlorine consists of two common isotopes, C35 and C37. And we've got 75% of which is Cl35. The mass spectrum of A was recorded when A was ionized by electron impact to form A+ ions. Draw on figure 3 the peaks for the molecular ions in the mass spectrum of A. So we've got the chart there. So the easiest way to do this is initially just count up how many carbons you've got and multiply that by 12. Count up how many hydrogens you've got and multiply that by 1. Then add them together. So we've got our basis of the structure without chlorine. So then we know that some of this structure is going to be with Cl35. So with the number that we've just got by adding all the carbons and hydrogens, we can add 35, and that gives us 134. So we know that we're going to have a peak here. And instead of adding 35, if we added 37 from the other chlorine, that gives us 136. So we know that we're going to have two peaks, one at 134 and 136. But because 75% is Cl35, so that leaves 25% for the Cl37, we know that the relative abundance, we're going to have 3 times as much of the 134 as we are the 136. So if we draw a line there that's 3 segments big and a line there that's 1 segment big, that takes into account the relative abundance of each. Okay, reaction of A with warm dilute aqueous sodium hydroxide forms an alcohol, B. Name the mechanism for this reaction, outline the mechanism using the structure of A shown, and include the structure of the product alcohol B. So the mechanism is going to be nucleophilic substitution. So now we've actually got to draw the mechanism when it reacts with sodium hydroxide. So we're going to have down here an OH species. And first thing that's going to happen is we're going to have a curly arrow going from the lone pair on the OH to the carbon of the C carbon-chlorine bond. So if we draw a curly arrow. So one thing to note when you're doing curly arrows is make sure that they start and end either right in the center of the bond or at the atom, so the examiner's in no doubt where the curly arrow is going to and from. So next is we're going to have our curly arrow going from this carbon-chlorine bond to the chlorine, like this. Okay, so that is going to give us a structure of the C and the 3 hydrogens. It's going to give us our carbon and another carbon up there. This is the carbon that's now got the OH attached. And then we've got our next carbon with the methyl group, and then we've got our final carbon. So just put on all the hydrogens. Well, I'll just draw the lines so you can see what's going on rather than actually drawing all the hydrogens individually. So that will be our species, that'll be our alcohol with the hydroxide substituted where the chlorine was. So next part was reaction of A with hot ethanolic potassium hydroxide gives alkene C. Name the mechanism for this reaction, state the role of the hydroxide ions, and outline the mechanism using the structure of A, and include the structure of the product, alkene C. So our mechanism is going to be elimination. And the role of the hydroxide ions is going to be a base. Okay, so again, if we start with our hydroxide ion down here, and our first curly arrow is going to go from the lone pair to the hydrogen, and it's the hydrogen on the adjacent, on the carbon adjacent to the carbon-chlorine bond. So next curly arrow is going to be from that carbon-hydrogen bond to that carbon-carbon bond. Then we're going to get a further movement between this bond and the chlorine. So all in all, the structure we'll end up with is our carbon down here. We've got another carbon, and this is our methyl group. Then we've got our double bond there. We've got our next carbon with a methyl group, and then we've got our final carbon. (6.5) gives us an infrared spectrum that's either of alcohol B or alkene C. And what we've got to do using the data on our data sheet is work out which is the correct compound. So it's either going to be alcohol B or alkene C. So what we need to do is look to see whether it's got peaks for the OH bond that you'd expect in an alcohol, or the double bond between carbons that you'd find in the alkene. And in this case, we can see the double bond between carbons because we'd expect a peak between 1620 and 1680, which we've got. But if we add the OH group from the alcohol, we'd expect a peak between the 3230 and the 3550, which we haven't got. So our answer is going to be alkene C, and our explanation is because we have a CC1620 to 1680 per centimeter peak, but no OHP at 3230 to 3550. So the last part of this question says compound D reacts with dilute aqueous sodium hydroxide in a similar way to A to form alcohol B. Explain why D reacts more quickly than A with dilute aqueous sodium hydroxide at the same temperature. So we can see the differences between these two structures is we have a chlorine here, whereas we've got a bromine there. So we've got, why does compound D react more quickly? So some students in the exam start talking about the reactivity of bromine compared to chlorine, but that's not the case why it reacts more quickly. It's all to do with the strengths of a carbon-chlorine bond compared to a carbon-bromine bond. So we can say that CBr is weaker than CCl bond. And because it's weaker, therefore it's going to break more easily and therefore reaction. Question 7 asks us to identify 4 compounds. They're all colourless. It says 2 of these compounds can be identified using different test tube reactions. Describe these 2 test tube reactions by giving reagents and observations in each case. Suggest how the results of a spectroscopic technique could be used to distinguish between the other 2 compounds. So during the exam, many students approach this question as if they already knew which compound was which. But you know, you don't. You've got to write as though you're starting with 4 compounds or 4 solutions that you've no idea what they are. Also, some students used potassium dichromate, but didn't realise that you could that 2 of the solutions gave the same result. And also a few successfully identified 2 compounds using the test tube reactions, but didn't explain how the spectroscopic techniques could be used. So the way to approach this is what we would use, for example, acidified potassium dichromate, and in turn add each of the 4 solutions. So we'd start with acidified potassium dichromate. Now, 2 of the solutions would end up going green, so we'd end up with the solutions that went green with butanol and butan 2-ol. And the other 2, so we get no reaction in the other 2. So now we've got 2 sets of solutions. We've got 2 solutions that have gone green. Either of those could be butanol or butan 2-ol. And we've got 2 solutions that didn't react, which could be the butanone or the 2-methyl propan 2-ol. So for the 2 that had gone green during this reaction, so for 2 solutions that went green, we're now going to use Fehling's reagent, and that will give us the 1 will give a orange-red precipitate for the butanol. So we've identified the butanol because what we've done is we've taken the 2 solutions that had gone green. The one that now goes orange-red is butanol. The one that doesn't react, so the other, is butan all. So we've identified those two solutions by test tube reactions. So we're left with two solutions that we don't know, that we've got to use spectroscopic techniques. So for this we could use mass spec on other two, because they're going to have different MR values as diff MR values. So we'd expect to get a peak for butanone at 72 and for 2-methyl propan 2-ol, we'd get a peak at 74.0. So now the two peaks, the two solutions that we couldn't identify using test tube reactions, we've able to distinguish through mass spec. Other than mass spec, you could use infrared spectroscopy to identify the different functional groups. So for example, again, you'd have an OH group between 3230 and 3550, or a C-double-O bond between 1680 and 1750. I could also mention that if they didn't have different functional groups, you could use the fingerprint regions against known compounds. Question 8 tells us that methanol can be manufactured in a reversible reaction, as shown in this equation. So state and explain the effect of using a catalyst on the yield of methanol in this equilibrium. We're using a catalyst. Yes, it increases the rate of reaction in the forward direction, but it also increases the rate of the reverse reaction. So it has no overall effect on the yield. So we can say no effect on yield, as it increases the rate of forward and reverse reactions equally. Now we've been asked to give an expression for the equilibrium constant Kc of this reaction. So if we have a look at the equation again, so we've got carbon monoxide and H2 on the reactant side, and on the products we've got CH3OH. So remember, we've got 2 there for the H2. So if we write out the Kc, we've got Kc, so then we've got the concentration of our product, so that's CH3OH, over the concentrations of our reactants, so that'll be CO and H2. And because in the equation we've got this 2, in our Kc equation we make sure that is squared. So common errors that students would do would be to forget the square brackets and forget that 2 there. So question 3, a mixture of carbon monoxide and hydrogen was allowed to reach equilibrium in a container of volume 250 cubic centimeters at temperature T. At equilibrium, the mixture contained 0.340 moles of carbon monoxide, 0.190 moles of hydrogen, and 0.0610 moles of methanol. Now remember, in our equation it's about concentrations, where these are absolute amounts. So to convert our absolute amounts into concentration, we have to divide by the volume that it's in, and in this case 250. So for example, the concentration of our product becomes 0.0610, which is the absolute amount of methanol, divided by the volume that it's in. So this is 0.250. And underneath would be the concentration of our reactants. So it would be 0.340 for the carbon monoxide, again divided by the volume that it's in. So 0.250 to give us the concentration of carbon monoxide, multiplied by 0.190 divided by 0.250 to give us the concentration of hydrogen, and remember, that's squared. So that gives us a value of 0.244 divided by 1.36 times by 0.76 squared, to give us a final value of 0.311. So a final part of this question says the methanol decomposes on heating in a reaction that is the reverse of this. So we've given the equation there. Use your answer from question 8.3 to determine the value of Kc for this equilibrium at temperature T and state the units. Okay, and you're given some numbers in case you hadn't managed to calculate it before. So what we have to find the Kc, so Kc equals 1 over Kc of the reverse reaction. So it'll be 1 over 0.311, which you just calculated. So that's going to be 3.22. So to work out the units, what we've got now is we've got basically 3 lots of concentration on top and 1 underneath. So we've got a mole per dm cubed from the first reactant, so in this case so first product, which is carbon monoxide, and we've got our concentration of hydrogen, which is mole per dm cubed, and that is squared over a mole per dm cubed from our methanol. Now this is going to cancel out with that one, so we're left with a mole per dm cubed squared. So if we square out the brackets, that becomes mole squared to the dm minus 6. Question 9 says a student has a 10 cubic centimetre sample of 1 times by 10 to the minus 2 mole per dm cube methanoic acid solution. The student is asked to dilute the methanoic acid to a concentration of 2 times by 10 to the minus 4 by adding distilled water, which volume of water should be added. So it's going from 1 times by 10 to the minus 2 to 2 times by 10 to the minus 4, which is a 50 times dilution. So the dilution will be 1 in 50. So because we've got 10 cubic centimeters, 500 times that will be 50 times that will be 500 cubic centimeters. Which molecule does not have a permanent dipole? So that will be D, because it's symmetrical. Which is the major product of the reaction between 2-methyl-butene and iodine monochloride? So with this, remember that the I and the Cl are going to go to either side of the position where the double bond was, which is in position 2. So the answer to this one is C. Which statement is not correct about the industrial preparation of ethanol by the hydration of ethene at 300 degrees C? So we can see that it's an exothermic reaction. So the higher the temperature, then the higher the yield equilibrium of ethanol. Which compound has the highest boiling point? So this one is B. Now a lot of students during the exam thought the answer was D, because I think that they thought that there was a number of hydrogen bonds between the molecules, but that's not the case. Which statement is correct about the fractional distillation of crude oil? So each fraction contains a mixture of hydrocarbons. How many structural isomers with an unbranched carbon chain have the molecular formula C4H8Br2? So if you just spend some time just sketching different structures with this formula, then you come out and should get 6. The Maxwell-Boltzmann distribution of molecular energies in a sample of gas at a fixed temperature is shown. Which letter describes the mean energy of the molecules? So remember, we've got energy along here and number up there. So it's going to have to be C or D. Now C is the maximum, the energy where we have maximum population, and D is the mean energy. Ethanol can be made from glucose by fermentation, and we're given the formula there, but again note that we've got a 2 there. In the experiment, 268 grams of ethanol were made from 0.44 kilograms of glucose, and we're given the molecular weight of each. What's the percentage yield? So what we need to do is find out how many moles there are of each. So if we work out the number of moles of ethanol, so that would just be our 286 divided by 46, and that comes out to be 5.83 moles. And how much glucose we started with, and again that'd be 1.44 divided by 180, so that would be 8. So percentage yield, so given the number of moles of ethanol, but remember, for every mole of ethanol, for every mole of glucose we started with, we'd expect 2 moles of methanol. So then it just becomes a division of what we've actually got divided by what we expected, and we come out with 36.4%. Which species could act as a nucleophile? So again, it's just knowing the properties required of nucleophiles. So this is pH 3. Which statement is correct about polychloroethene? And with that one, its brittleness is reduced by plasticizers. So again, it's just knowing about properties of different polymers. So here, what's the enthalpy of formation of buta-1,3-diene, C4H6? And we're given the enthalpy of combustion of each of these. So the shorthand way of doing it is, we know that we've got 4 carbons, so it'd be 4 times by 394. We know that we've got 6 hydrogens, so it'd be 3 times by 286. Add those together and it comes out to be 2434. Now we've got the enthalpy of combustion of buta-1,3-diene is a greater minus number, so that means we're going to get a positive value, and the difference between the two values is 112. So our answer is going to be plus 112. A gas cylinder contains 5 kilograms of propane. How many propane molecules are there in the cylinder? And we're given Avogadro's constant. So for this one, what we need to do is work out how many moles are in 5 kilograms of propane. So the molecular weight of propane is 44. So our calculation becomes 5,000. So because we've got 5 kilograms, so it's 5,000 grams divided by 44, which is our molecular weight of propane. So this will give us the number of moles of propane we've got, and then multiply that by Avogadro's constant to give us the number of molecules, and that comes out to be 6.8 times by 10 to the 25. Which sample of liquid has the greatest volume? So here we just calculate the volume of each of these by, for example, if we've got 500 mgs, so that's half a gram, it would just be working out the volume that half a gram would take up, so it'd be 0.5 divided by 0.63, and the same calculation for each, so it'll be the mass as 650 or 0.65 divided by 0.8. And if we do that calculation for all 4, with C we end up with 0.9023, which ends up being the largest out of the 4 volumes. And lastly, we've just got to know about what an initiation step is. So we're given 4 reactions, and the initiation step that is listed here is the final one, D.